You came back for the second part. So that's a good sign. What we're going to be talking about now is something that kind of builds off of the idea of a reaction rate. And it's something called the rate law. And I would say that this is probably the fundamental piece of kinetics that you need to be able to know how to do. So we're going to kind of get into that. So what the rate law tells us is it tells us the relationship between that one factor we talked about before that affects reaction rate, which is the change in concentration. So what I mean by this is it's like, hey, if I double the initial concentration of my reactants, what's going to happen to my rate? Is it going to stay exactly the same? Will it double? Will it quadruple? Like, how the heck is that going to change? And so that is really important when we are trying to take a look at chemical reactions, especially if you are, let's say, a chemist who is trying to, create a product. You need to know how changing that reaction is going to affect something, especially if you need to mitigate like heat or things like that from an exothermic reaction. So the rate law is really important. Now, in terms of easiness, there's some math that has to be done. So it is not as easy as taking a look at the coefficients in front, like this reaction, and saying, oh, this is going to make it go 3 times faster because it has a mole ratio of 3. That is not how this necessarily works. And it really depends on the nature of the mechanism that we talked about first. So it's like, how does this connect? In what way? And that is really what's important. After we get to learn rate law, we will tie this back into mechanisms, and I'll show you what I mean by that. So if we look at an overall reaction like this here, these coefficients are not important when we're talking about the rate law. If we're talking about a mechanism, it's a different story, but we'll, like I said, save that for later. What the rate law actually looks like is this. Now, this is obviously a generic form because we're talking about chemicals A and B. So whatever we're talking about, those chemicals go in there. If you notice, it's only dependent on the reactants, which makes sense, right? Because the reactants are the things that are going to control how fast it happens because you've got those things changing into your products. So its rate equals this K value here. And then remember that the brackets equal concentration of A to the Y power and then B to the Z power or whatever variable you want to insert there. Okay, we'll get into more specifics right now. So when we talk about this, the rate is literally the rate that we just talked about, the change in concentration over time. So that's going to be dependent on the data that's given to you, so just be careful with the units on that. Now, K is something called a rate constant. And a rate constant is a unique variable that is for each reaction at each temperature. So it is like very specific to a reaction and the temperature it's occurring at. And basically, it's just how that is going to be changing with respect to your different reactants. The thing about a rate constant that's annoying is that the units are specific to the actual reaction. And you'll see what I'm talking about when we go through the example. Okay. Now, A and B are the concentrations of whatever those reactants are, and usually that matches the unit in the rate. And then Y and Z are what we call the reaction order. So the reaction order is essentially how it is affected by that change in concentration. And I have only on the exam ever seen whole numbers there. And most of the time you're going to see a number between 0 and 2. I haven't seen anything that you've had to calculate that's had a higher order than 2, but it in theory is possible. So that's going to likely be a whole number that's going to show you how that thing is affected by concentration. So what that means is if you see a 0 order in a reaction, what that means is that that particular reactant, no matter how much I change the concentration, so if I double it, triple it, whatever, it's not going to matter how much I change it. The rate's always going to stay the same. And there are some things that actually that happens for. So there's a 0 order reactant where no matter what I do, it will always go the same rate because of how it reacts. Okay. If you get a 1 for that little superscript at the top, that's called a first order reaction. And what that tells you is that if you would double the molarity of your reactants, you would expect to get a concentration or a rate change that's twice as fast as well. So if I double concentration, rate doubles as well. And then if I have a second order for my superscript there, if I double my concentration, it actually makes my rate go quadruple. Okay. Now, when we go back to our rate equation here, The sum of these two things here is the overall reaction order. So if I have a 2 and a 2, my overall reaction is what we consider fourth order. But I don't know if you're going to have to answer that question, but it's not going to hurt to know. Okay. So like I said, overall reaction order is the sum of those exponents. Now, what does this look like in real life? What happens is the technique that we typically use is called the method of initial rates. And like I said, at the beginning of our chemical reaction, that's when things are happening the fastest. So they measure the rate at that kind of short period of time at the beginning where you see the most dramatic change. And what they do is they figure out the rate. So they measure change in concentration as time changes, and then they get a rate value. And what they'll do is they will set up a number of trials with different concentrations that are, vaguely related to each other. So in this case, I've got trial 1. I got my rate here. Note the units on this are moles per liter per second. So it's how the molarity is changing per second, but this could be minutes or hours or whatever. And my first trial is 0.1 molar and 0.1 molar. My second trial has a different rate now, but I have a 0.2 and a 0.1 molar. And my next one is a same rate as the first one, but I have a concentration that's 0.1 and a concentration that's 0.2. So what you're going to do is you are going to have to take a look at this data and analyze it to figure out what is going on with the orders. And so what we will do is we will investigate each of these individually and then figure out the order and put it into a rate law. So what we're going to do is we're going to determine the order for the reaction 2A plus B turns into A2B, and then determine the K value, including units. So this is the example we're going to work through. So I'm going to go to my doc cam now. Sorry, I'm struggling a little bit here. Okay, so click off of that. Open this up for you. Okay, so when I am looking at this, I need to think about what my generic rate law is going to be. So generically, it is going to be rate equals K, and it's always rate equals K, and then it is times the concentration of A. Now, if this were an actual chemical, we'd put the chemical in here, to the X value, times B to the Y value. So it's always a multiplication with each of these. If I had 3 reactants I was looking at, it would be multiplied by whatever that particular thing was. But we only have 2 in this case. And so what we want to do is we want to set up a ratio to see if we can figure out what happens when we do change those concentrations. And what I like to do and what they recommend is by taking this generic equation here and plugging in different values to figure out what that ratio is. And to do that, what you want to do to decide which trials I'm going to compare, the easiest way to do that is to select, if I'm looking for figuring out how A is going to change, I'm going to find a trial where A is different from one trial to the other, but B is not different. So if I can find that, that's what I want to do. And then I'm going to set up a ratio. Now, it is up to you how you want to set this up. You can set it up with either of these on top or bottom. To make my life easier, I tend to pick the number that's bigger to go on the top for the ratio because I just think it makes the math a little easier. So I'm going to do a ratio to figure out A of trial 1 and 2. But I'm going to put trial 2 on top and then put trial 1 on the bottom because 2 is bigger than 1 for its rate. So what I'm going to do is I'm going to plug in these values into this generic rate law. I do not know X and Y. That is what I am trying to figure out by doing this order. So you'll kind of see what happens as I go along here. So the rate for trial 2 is 5.45 moles per liter per second. And that is equal to K times, now this is concentration of A. So I know that A in trial 2 is 0.2 molar, but I don't know what this exponent, my order, is. I'm going to multiply that by the concentration of B in this trial, which is 0.1, to the Y power. Okay, so this is just the generic setup of this. That's all the stuff for trial 2. Trial 1, then, I'm going to repeat this, but I'm going to use the data for trial 1. So it's 2.73 moles per liter per second. That's equal to the same K value. Now the K value, because it's a constant, should be identical regardless of the trial you do, is equal to 0.1, because we've got a 0.1 molar here to the X power, and then again 0.1 to the Y power. Now the reason you want to pick the trials because of that, in that particular way, is because of this. So what's going to happen is, if you see here, the terms 0.1y and 0.1y are the same. So if I have identical terms here, I can cancel those out. And then units of moles per liter per second go away as well. And I am being a delinquent here. These are technically units of molar. Now, I leave them off because the College Board isn't necessarily super fussy about that, but it will be very important when we're figuring out our K values. So if you set it up so that you've got just numbers here instead of molarity, I am not going to lose sleep over that. But let's investigate a little more here. So if we look, 5.45 divided by 2.73 gives me right around the neighborhood of 2, right? So this is about half of this. K values are identical, so those cancel out. And what I'm left with is a ratio of 0.2 over 0.1 to the X power, which, if we do that math, is going to be 2. So 2 equals 2 to the X power. Now what this is telling me is that if I have double the concentration, my rate is double. And so if you think about what number X has to be to make that true, X has to be 1, which means that it is first order. So a first order reaction is where I change my concentration, like double it, and I double the rate. If I would quadruple my concentration, I would quadruple my rate. So that is the definition of first order. So when we fill in our rate law, X is going to be 1, okay? Hopefully that made a little sense. We will see when we get our overall rate law figured out. So for B now, we'll go back here. For B, I want to figure out what the order is for B as well. So I'm going to do the same thing. I'm going to pick 2 trials that are the same for A, if I can find it, but different for B. And if we look here, 1 and 3 work really nicely for that. So I'm going to put, in this case, if we look here, I don't have any difference in rate, so it's not going to matter what one I put on top here. So let's do trial 1 over trial 3. Like I said, I normally like to put the bigger number on top because then it just makes it not a fraction, because fractions are a little nasty here. So trial 1, its rate is 2.73 moles per liter per second, and that is equal to K times the concentration of A in this trial is 0.1 molar. Okay, now I already know the order. I'm going to put a little 1 there because I know what that is. If you didn't know it or you didn't want to put in there, if I would leave this as an X, that should work as well because they should cancel out, but not a big deal. And then my concentration of B is also 0.1 molar, but it's to the Y power because I don't know what that is. Remember, I could put these M's there, but again, they're not super fussy about that part. Okay. Trial 3's data, my rate is 2.71 moles per liter per second. So hopefully you're looking at this already and you're saying, well, their rates are pretty much identical. Hopefully in your mind, that's already tipping you off to what kind of order this is. So I did my data selection nicely so that these 2 numbers cancel out. And then I've got 0.2 molar to the Y power. So if we think about what's going to cancel out here, the moles per liter cancel, the K's cancel, these 0.1s cancel. And so what I have essentially is these 2 numbers divided by each other, which is basically 1, equaling 1/2 to the Y power. And if you think about what number I've got to put here in my exponent to make this true, what do I have to put this power as to make half equal 1? It's going to be the 0 power. So this is what we actually call 0th order, which kind of sounds funny, but that's what that is. So it asked me to determine the rate law. Now I know my 2 orders. So my actual rate law is going to be rate equals K times the concentration of A to the first power times the concentration of B to the 0 power. Now, you wouldn't have to write it that way. You could also write it as K times the concentration of A and just leave the B out. But for my own like data keeping and record keeping, I like to keep the 0 power there. So this is considered our rate law. And so what this tells me is that even though I have a coefficient of 2 here, it doesn't mean anything. It just means that if this coefficient means nothing relative to this order that we see here. So what this rate law is telling me is that the speed of my reaction only is going to depend on the concentration of A. I can change B's concentration to whatever the heck I want, and it's not going to make a difference. It also tells me that if I double the concentration of A, I should expect my speed in my reaction to double as well. So that is what that's telling me. Now, the other part asked me to find K and get units. So what happens is this is all fine and dandy here, but this rate constant is going to be important because it's going to tell us in what way it's going to change as well. So that kind of gives us our how it's going to change the numerical relationship. The nice thing is this is constant regardless of which trial you use. So pick whichever one is your favorite. I'm going to pick this one because it is the one I can kind of fit on the screen here a little bit. So that's the one we're going to use. So you're going to pick the rate and you're going to put that into your trial. So I have the rate equaling 2.71, and that's moles per liter per second. Okay. Now this is where the units are super important. That is equal to that constant that we are trying to figure out times the molarity of A, which is 0.1 molar to the first power, times, and this is why I just like to put it in there, molarity of B to the 0 power. And I forget that unit here. Okay. So when we think about this, numbers are important as well as units. So these units here are moles per liter per second. K is here. The units on this guy are, it's 0.1 molar. And then because this is the 0th order, that's going to make that go away, and that's just going to become 1. The units on this M also become 1, and it's just 1. So if I want to solve, I'm going to divide both sides by 0.1 molar. And that's where things kind of get a little funky with this K business. So if you think about how the units work out here, this moles over liters is the same thing as M, moles over liters. So when I talk about the units on here, the moles per liter can cancel out, but the seconds on the bottom don't. So if I take 2.71 and divide it by 0.1, I get 27.1. And then the units on that are 1 over seconds, and that equals my K value. Kind of weird, but you could also write that as 27.1 seconds to the negative 1 as well. So rate constants, and this is the strange part, they are always asking you questions about the constant, but the unit is changing as well. And the unit depends on these powers here in our orders. So what I mean by that is this. I'm going to flip this guy over here. So your rate is always going to be some concentration over time. Like let's say I have moles per liter per second, or you could write it as molar seconds. My rate is always going to be something kind of like this. So when I set up my equation with my rate law, whatever this unit here happens to be, you will have units of molar and then whatever powers your orders are. So let's say for this one, I have one that's a third order and one that's a second order, just for an example here. Okay, so my equation needs to work out so that my K value gets rid of all of these molar units here except for 1. Okay, so molar seconds equals this K value times molar to the 5th power. And so the K's units are designed to knock out units and make time show up. So your K will always have a unit of time in it in the denominator somewhere. But then the whole purpose of it is to make whatever molar units I have here equal to 1. So you could write it like this if you wanted to, molar to the -4th, and that would give us molar to the first power. You could write this as 1 over molar to the 4th seconds, because then if I take that times 5, they'll cancel out and I'll only have 1 molar left. Or if you wanted to, you could write it as liters to the 4th over moles to the 4th seconds, and all of those are the same thing. So rate constant units are kind of their own weird little animal when we talk about this. So remember, when you set up your K values units, it always has to be, these all have to add up to 1 molar on the top and a time component on the bottom. Okay, so we will kind of discuss that a little bit more at length when we get together. If you have any questions, please make sure you get them cleared up. Otherwise, good luck.